I had to do that the other day because when they changed it, all of the navigation was on the right side, not the left side.
Yeah. Life with browsers and such. Spin 2 for beginners. Week 5 files available now. I think I found your post, John.
Okay, cool.
Okay, JonnyMac, I made you co-host.
Okay. Guess I should turn on my camera now. Whoops.
Hello.
Wow. What's going on with my green screen? Clearly, it's wacky.
It's green.
I'm just muting people, and please do unmute yourself to say anything. I'm just doing a little bit of microphone management for you while we get set up here.
What's going on?
Well, John, I'll take care of some things while you get going.
Okay.
Everybody, welcome to the Propeller 2 Live Forum. Today's January 27th. It's 4 p.m. Pacific, later or earlier, wherever you are. And today, JonnyMac is talking to us about serial peripheral interfacing with the MAX7219 and the P2 Edge's 16 megabyte flash. And this is I think the 6th series we've done, or 6th event.
No, it's number 5 today.
Is it 5? Okay.
Yes, yeah.
Just having so much fun that I can't count anymore. Today, so we'll spend an hour on the topic. John's going to talk the whole time, and I think we can interrupt him if we have really quick questions, but we can't sidetrack him because he always has a lot of valuable things to say. And then afterwards, we'll take 30 minutes of Q&A type questions that are on topic. And I'll try to keep that going so we don't stray too much. This is a rated G event today, so keep that in mind.
Darn it.
Yeah, well, troublemaker. And while John gets going, what you could do if you have the hardware today, the P2 Edge, is really all you need, just be able to program that. But it's really nice to have a few more parts that I'll show you. You can go to the forums, to the link I just pasted in the chat, and then download the week 5 files. And there's a lot of stuff there. So it goes in your library and your code directory, or you can put it all in the same folder. So you can go grab that. And then for those watching the video recording, there's something you can read off the screen here, but I'm linking these back to Quick Bytes and other places so resources are not lost, trying to at least. The hardware we're using today, here's some micro pictures of stuff. Some of it's actually really big, but we're using the P2 Edge, or you can use a Propeller 2 evaluation board. Cheapest way to get going if you're new to this is the P2 Edge and then the mini breakout board. But there's actually a version that'll plug into a breadboard as well that's only $7. And then you need a prop plug, which I've not shown here too. Those are $14. But my favorite hardware is this board in the middle that's like bigger than a big sandwich. And it just holds everything. And it's called the JonnyMac. And then we're also working with this MAX7219 8-digit 7-segment digital LED display, and those are really cheap on Amazon. I think you get 2 for $8 or something, or $6. And quality may vary on that, but they're just a demonstration tool, and they're just fun to work with. Even though it's not alphanumeric, today it kept me busy for about 2 hours, so it's fun. And where do you find things afterwards? We are starting to collect up and post the examples that are shared all over the place on this link, which I'm pasting in the chat. You can just go to parallax.com and look for the P2 Quick Bytes. And I think we have 10 of them now. We're going to be adding today's content and then the I2C LCD. And then at some point we'll be moving into stuff that's really impressive, Propeller. But these are all actually using Smartpins and some neat Propeller features already in the lower level objects. So you'll see when you dig around or if you watch the videos. getting started today. If you want to be like me, or maybe you don't, you can go over here to JonnyMac's website, and I encourage you to make a deposit to the Bank of JonnyMac. And when you do this, sorry, John, call it a gift when you use PayPal, because it just goes through a lot easier. And really our goal here is to keep JonnyMac unemployed so that he works for all of us. Because if he gets a job, we don't really want that to happen. So don't let me be alone, and throw some money in there, whatever you got. Or if you can't, that's fine too. But John saves us so much time writing code and gives us a lot of valuable information and helps on the forum so much. I just really want to encourage that. I think we're all very fortunate to have him on our side. Otherwise, imagine the pressure on Chip. It wouldn't matter anyway. He's like a cat. So, all right, John, you got something to talk about?
Yes, sir. Well, I apologize, everybody, for that thing. Normally that gets separated, and the other day it was working fine. I don't know what's going on with Zoom today, but I'll just switch over to sharing so we can get going right away on the presentation, and that way we won't have to be looking at my silly green screen. So today we are talking about SPI, or serial peripheral. Boy, I just lost. I'm trying to do two things at once. Let me just do a share and we'll get going. Forgive me. SPI stands for serial peripheral interface. Are you able to see my my screen?
It's just right.
Okay.
Yes, I see it.
Okay.
It's there.
Yep. Okay. Thank you. So SPI is serial peripheral interface. It's kind of the grandfather of the chip-to-chip communications mechanisms that we used. And we actually kind of started with newer stuff, and now we're kind of going back in history. But SPI is still widely used. It can be very fast. One of the difficulties you'll see is wires. So we'll just go through the normal kind of structures we did the last couple of weeks and jump into some code. So as I just said, SPI stands for Serial Peripheral Interface. It was created by Motorola in the mid-1980s, and it can be half duplex or full duplex, and it uses a bunch of wires. It's also synchronous, which you'll remember when we said something is synchronous, it has a clock that is controlling the data. So in the SPI transaction schemes, there is a single master and multiple slaves, and the master always controls the transactions. You'll see a lot of devices that we use SPI, even if you weren't aware that that was happening, that are not even intelligent devices. Things like shift registers and really simple chips like that, that can use simple digital state machines. They work really, really fast. And that is one of the advantages of SPI. It's very fast. Many microcontrollers that are available today have SPI hardware built into them. We don't in the Propeller, but that's not a problem for us because we can synthesize SPI to do anything we want. The P2, additionally, over the P1 has Smartpin modes that support SPI and give us very fast communications without a lot of code. So one of the things, as I just pointed out, SPI uses a lot more I/O than other connection schemes, and we'll see that. This is a diagram you may have seen on the internet or elsewhere. It's a very common looking interface. So this is the master controller, and these are slave chips. They're, the devices we're talking to. Now, you'll notice in SPI, we have, if we're talking to a SPI device and we're going to get data back, we're going to have at least 4 pins. So that's where we're starting, is with 4 pins. Now, if it's a half duplex device and we're only sending it information or only getting information back, then we would be down to 3. But on a full implementation of SPI, it's 4 pins for the first. Now, for each additional slave, we will add another pin. So let's go through the pins we were just talking about. S clock is SPI clock. That is the clock that is synchronizing the data in the streams. This is an older label, but it's very clear. It's MOSI, stands for Master Out, Slave In. So there's no doubt what's going on that line. It's data from the master controller over to the slave device. The complement of that is right below. It's called MISO, which is Master In, Slave Out. So this is where the slave is sending data back to us, is going to come through that pin. And then for each device that we have in the configuration, our design, we need a slave select line. You'll notice, for those of you that are new, if you've not seen this before and you're wondering why there are little lines over SS1, SS2, and SS3, that's indicating that these are active low signals. What that means is to turn off, I'm pointing at my screen as you can see it, to turn off these devices, we're going to make their slave select line high. To turn them on, and we only can have one on at a time unless we want problems, we're going to pull that line low and then do the transaction. So does that make sense to everybody? I mean, it's pretty straightforward. Clock takes care of synchronizing the data. MOSI is from us, the propeller, out to a device. MISO is from the device back to the propeller. And the slave select is which device of multiples, if we have them, that we want to communicate at a given time. Everybody okay with that? It's pretty straightforward stuff. Now, there is another SPI configuration that you will see. And you have to look at the wires closely. So in this configuration, I'm saying it's daisy chained. Notice the clock goes to everybody. So the clock goes here and it comes down to here and here. So the clock is the same configuration. It's parallel to everybody. Everyone gets the same clock. But look at the MOSI pin. MOSI goes to the MOSI connection on the first slave, and then the MISO connection on that slave goes to the MOSI pin on this second slave, and so forth and so on. So, and then you wouldn't normally see this full loop configuration. I'll explain in just a second, but if we were doing input type devices, the MISO comes back from the last slave, comes back to the MISO pin on the master. And in this case, there is a single slave select because we want them all to be active at the same time. So what happens is, and here I'll give you a real world example, not that board, but this board. Hopefully this will show up against my skin. Oh, it probably now my green screen thing's not working. So this is a board that has some digital inputs right here. And there are two chips, one there and one there, that are parallel in, serial out shift registers. What this does is it allowed me on this design, because this is a P1, we don't have as many inputs. So by using two 75 HC165 shift registers and linking them together this way, I can take 3 pins on the propeller and get 16 inputs. Now, they're not live real-time inputs, but this is an industrial type controller, and I have background code that reads the inputs every millisecond, which is plenty fast for what we're doing with this device. But what that allowed me to do is using SPI devices, in this case, the 74 HC165 input shift registers, I was able to create 16 inputs out of 3 propeller pins. And again, the way those work, now in that case with the 165 shift register, it has what's called the slave select is not really a slave select in the normal SPI sense. It's a load line. So you blip that line and the shift registers will latch whatever is sitting on their inputs to an internal register. Then when we start clocking the data, in this case, I have to send 16 clocks, that sends all the data from the 2 registers back into the propeller. And so this is a type of SPI configuration, but we're using daisy chained. The opposite side of that is using a shift register, another really common part called a 75 HC595. That's an output shift register. And so with that and a little bit of code, you can take 3 lines and turn it into technically up to 32 is probably a practical limit that I would ever do. And I did that once for Disneyland, where they needed a whole bunch of outputs from a propeller board. So we used 595s, and we were able to take a long and shift it out, and that aligned itself into the 4 devices. So with 3 outputs, we turned that into 3 outputs from the propeller. We got 32 outputs from the 595s. With a little bit of coding, I was able to write an assembly cog that could run very fast, since SPI is fast anyway, and do low frequency PWM over those 32 outputs. It was, right around 100 hertz, so not very fast in the scheme of PWM, but it was enough that it didn't cause any flickering, because these were controlling LEDs in a big lantern project that Disneyland was building for some of their hotels. But again, so if you see those are really common parts. If you don't have them in your parts store, you ought to get some just to play with. The 74HC165 and the 74HC595. So the first is input, the other is output. And so I actually didn't have a chance to squeeze it in. So I'm going to switch over to a drawing program that I use. And these are the normal configurations. We have MOSI and MISO. I'll change that in just a second. Let me talk about, when we're doing creating the signals, you'll read when you look at devices, their SPI mode. Now, thankfully, most of the devices that you'll run into will be what are called mode 0 devices. Now, the mode is defined by the polarity of the clock signal and what's called the phase of the data sampling. It gets a little crazy, but I've got a diagram that will help make it a little more clear. So in mode 0, the clock level starts low and goes high to create a clock pulse. That's called clock polarity 0. So we start low there. Clock polarity 1, the clock starts high and goes low to create a pulse. So that's what's called clock polarity. And then the clock phase has to do with the alignment of the clock versus where the data is being sampled. In phase 0, the device that is writing a bit to the bus. Now remember, there's 2. There's the MOSI bus and there's the MISO bus. So the master is writing to the MOSI bus, the slave is writing to the MISO bus. In phase 0, then it outputs the data before the first clock, before the leading edge of the clock. And in phase 1, it does it after that edge. Again, this will make a little more sense. I'm only telling you this because you may run into it and I want you to understand it. Again, thank goodness, most devices we'll deal with, including what we're working with today, are in mode 0, which is with a clock polarity of 0, a high going clock, and the phase of 0, which means we stick the data out and we do a clock. Okay. So doing SPI on the P2, we have 3 ways we can go about it. We can write the code in pure spin, very easy. It's not as fast as the other modes because we're dependent on the interpreter and the clock speed of the device, that we're running, but it's very easy. The upshot is we can do a little cheat that I have done in times in the past, and we can do half duplex using 1 pin. Remember, a moment ago I was showing you those other diagrams, and we had a MOSI pin and a MISO pin. Well, if you're really short on pins, which in the P1 we often were, we could do this trick, and I'll show you here. Hopefully you're seeing my Inkscape screen. So here is a master that has a clock like we always do, and instead of a MOSI and a MISO pin, 2 pins, we're just using 1 pin, and we're calling it SIO for shift input output. Now, To do this trick, you have to insert a resistor right here between the MOSI and MISO pins of the slave, and you need to connect it in this way. This will prevent a problem if both things are trying to write at the same time. What I neglected to point out earlier is there are no pull-ups in SPI. It's driven. So when a device is writing a 1 to the bus, it's outputting VCC. When it's writing a low to the bus, it's outputting ground. There's no pull-ups in there. So if one is writing ground and the other one is writing 1, you could have a short circuit. This resistor prevents that problem. And then we still need a slave select. Now,
Hey, John.
Yes.
One thing about the SPI flash chips is that if you look at their timing diagrams, they will, according to the state changes, they will never create a conflict. And if you kind of do the dance with it, you can actually get rid of the resistor in applications where you want to just talk to a flash chip over 3 pins.
Okay.
But it is outside of the normal protocol, but the memory chips will work that way.
I am of the opinion that resistors are cheap insurance. So I always put the resistors in. And so, a use case that I've done many times, including recently, you may remember I was speaking about assisting my friend John with a target controller. And on that target controller, he has a joystick and several potentiometers that are read through a device called an ADC0838. It is a SPI device. We configure it like this because it's a half duplex device. You send it a channel you want to read, and then you give it more clocks, and it will output the value from that channel. But you're not, as with other chips it can do, you're not sending and receiving at the same time. So we cut down on the number of IO pins used. Now we can get away with that when we're using spin or we're using assembly, because we can change the direction of the IO pin on the fly. Now, I guess you could probably do this with Smartpins too, but then you're constantly reconfiguring the Smartpin, and I don't know if that, is going to be problematic, so I probably won't do it. But again, not really common, and with the P2, we're less constrained with IO pins, but if you do get into a pinch and you have a half duplex device like the ADC0838, which again, not needed as frequently anymore because we have ADCs built into the P2. This is a solution that is kind of a modified SPI. Okay, then as I was saying earlier, we also have on the P2 now, we have Smartpins capability. Now, Chip, based on my reading, it seems like we can only count on modes 0 and 2 because the Smartpins always are expecting data before the first edge. Am I wrong there?
I think that there is, I think I made the synchronous serial modes so that you can get the data before the first clock transition or after, and same for sending, I think. And I wasn't really thinking about SPI bus when I made it, but I knew that in some cases you're going to want to have the data there and grab it on the first clock, or you're going to want to have the first clock cause the first data bit to come out so that you can then register it.
Okay, I don't know how to do that, so that will be good because that'll make we can have then a universal driver using Smartpins, because Smartpins are very, very fast and we don't have to deal with the timing. We'll see that as we go through.
John, before you go any further, 2 quick questions that are in the chat.
Yes.
One is, are you sure the resistor's in the right leg? I would have thought the slave MISO should have it. Second question, I thought the resistor should be on the slave output.
Well, what we need to have is the resistor. Remember,
Barking at what's going on over here.
Yeah. You're right. Watch here. I'll fix this. Oh, I can't. Yes, you're absolutely right. Thank you for catching that. Because MISO is an output, isn't it? Forgive me. Yeah, it's slave out. Yeah. So.
Okay, we know they're paying attention now.
Yes, that's really good, and thank you for catching that. Here, I'll
while you fix that, I'll turn the barking dog off.
It goes. That's the correct way to do it. Thank you very much for. This is my fault for trying to jam in one more bit to the presentation 2 minutes before we're going live.
We're going to have to start giving out prizes.
I know that's really good one. Yes, thank you for that catch. That is absolutely the correct way to do it, because MISO is an output. It says so right there, and this could be an output mode. It says so right there. Thank you very much. All right, so here I won't get too heavy into this, but just so you understand these modes in case you incur. This graphic shows the relationship between the data and the clocks and where things happen. So remember, we're going to have this slave select no matter what. It's going to go low during our transaction. So this is when everything's alive, is while this is low. When the clock polarity is 0 and we're getting data on this first edge, that's called mode 0. And you see the little blue arrows I added. I found this diagram and then kind of cleaned it up. And the blue arrow is when the device that is putting something on the bus is when it should do that. So in this case, we're when we're doing clock phase 0, notice that the blue arrow happens before the first edge. In clock phase 1, here and here, the blue arrow happens after the first edge. And so you can see the red line is when the receiving side is sampling the data. This combination here is what we're going to see most of the time, thankfully. But if you happen to get a device, and remember, I always say, if you get a new device, get the data sheet. And if it says SPI mode X and you're not sure what that means, you can refer back to this in case you have to modify the SPI code or set it to a different mode. And here is an actual transaction of the flash chip that I captured a couple of days ago when I was playing with this. Now that the order of the signals is different than my diagrams. This line here is the chip select. So you're a slave select. So you can see it goes low during the transaction. Here is our clock. Now, if you look carefully, and I won't make you count, but I can tell you there's 32 clock pulses there. In this particular case, I'm asking to read a byte from the flash. And so the command for read is 3, which you probably can't see. This is very small, but that says 3 right there. That's these 2 bits. That's a 3. And then the other 24 bits are the address we want to read from. I don't know why, but in this particular case, I'm reading from address 1 in the flash. So that's an output command where I'm writing a command to the flash, and then the next 8 clocks will give me data back on the MISO pin, and this is the value. It was B6. So those are the 8 clocks to read that. And you notice after that, we're done, and so the slave select goes high. But this is what a transaction looks like. It's very, very easy. Now, you can have devices that will send data master to slave and at the same time get data back in. It's not very common, but one of the clicks that we have that I got to finish up some code for is called a MCP 2515, which is an interface for CAN bus, and it sends and receives data simultaneously. That's where the 2 pins come into play. If you have a device that is going to send and receive at the same time, you have to have 2 pins. Okay. Any questions? I mean, it's really not difficult, SPI communication. So that's really the crux of it, and we can get on to playing with code now if we'd like.
You could feel free to unmute yourself and ask if you don't want to type.
Yeah, please. Yeah, please feel free. I mean, this is a group. We're all friends. Let's talk. Okay. The first thing we're going to look at is this MAX7219 display that Ken, I think, put a link to, and I know many of you already had it anyway. This has this device. It's a multiplexing display driver that uses SPI, And because it comes up from time to time, I did a diagram that shows the wire colors that I use. Again, just as with my code, I'm very specific how I do formatting because it helps me see the code and find problems when they exist. I choose specific wire colors as well. So red and black makes sense for power and ground. I use white for clock and yellow for data, just like I did with I2C. Now, you're saying, okay, but there's two data pins because we have the data from the master and data from the slave. So this chip doesn't have data back, but in those cases where it does, I use orange for the MISO line. And then I use blue for my first chip select. If I have a second device, I use green. If I have a third device, I use brown. That way I can look at a breadboard that might have a lot of wires on it and know what's going on. Okay? All right. So if you have the code and the device, I used pins 8, 9, and 10, I believe. That's what I have on my breadboard. If you don't have to use these pins, but if you put it somewhere else, remember you've got to change the listing right here. And what I've done, you'll notice in the code, there are 3 versions of program 1. Program 1 does a little demo of this display. And let me say, because I know at least one of the people who participate in these sessions had a very old version of my MAX7219 driver. Please get rid of that and use the ones provided today because they're much friendlier. They have more features to them. I've added the ability to output single characters, strings, decimal numbers, binary numbers, hex numbers, do the normal stuff. And so if you run this code, Ken, are you able to show this code running on a
Sure.
kit?
Yeah, let me go
Let's
over
look
to that.
at it first and then we'll go through and talk about how we're doing the SPI and how the program is working.
Is that working right, John? I'm running
Yes.
program 1. Hey, there's our phone number.
Yeah, anyways, yeah, so here's where the demo is actually starting. Here's decimal output. Because of our system, it's right aligned, but you can start it in any column. Here's hex, the hex digits. Now you'll notice 7-segment displays are limited. You can't display all letters. So we live with it. Here's just individual segments and decimal points. And then we're back to, I don't know if I don't hear Roy's voice today, but if he's here, this will make him laugh because he knows more than me, but this is, you'll notice in code it's called Code Cracker. And every time I see this in a TV show or a movie where somebody plugs a card into something and a bunch of random digits go, and then suddenly the digits come on in random order, oh, we're solved. It's nonsense, but it's Hollywood, and I live and work in Hollywood, so now you know how to write a Code Cracker prop. Or you see the way I chose to do it anyway, using random numbers. So, you know, there's so many neat displays available that we kind of brush off 7-segment displays, but they're still viable because they can be very bright. They're very easy to see in across a room. And in many cases, we don't need anything but simple digits. I did a thing for an escape room in Dallas that was a big clock. So you can get these large, they're about 6 or 7 inches tall, 7-segment displays that have on them a 595 shift register. I was talking about that earlier, and some high current drivers. And so you can use SPI code to send the digit patterns out. So I made a giant wall timing clock for an escape room in Dallas using a Propeller 1 and 7-segment displays, really big ones. So Carol, it's easier for me to answer your question that I see it. I'm using Inkscape to do my diagrams.
All right, back at you, John.
All right, do I need to do the share thing again?
Yeah.
Can you tell me what an escape room is?
Oh, it's where you pay to be locked into a room and try to escape. It's a game. It's a puzzle solving thing.
Okay.
Yeah, no, people do it. And I know, especially people that I know in the IT and security world seem to like them because it's solving puzzles. Many of them are mechanical. Some of them are logical. And it's all about escaping from the room, you know, faster than anybody else does. But
It's great for team building.
yeah.
Yeah.
In fact,
Teenagers love it. Very
they're
popular amongst. Yeah, sorry.
No, sorry. Yeah, there's a delay. It'll be a popular pastime again once the COVID stuff goes away.
Yeah, we're all in an escape room right now that we can't get out of.
Yeah, yes, we are.
Nicely put.
I can't find the share button, Ken. All right. Oh.
Check the bottom middle of the
Yeah,
screen.
I was in full screen mode and it was disappeared. So with the MAX7219, it's a fairly straightforward device that has internal registers that we're going to write to. Some of them actually control the display elements. Others control things like the brightness, you know, which is one of the things we can set. So if you look at let me compile this so I can bring up this version of the display. So just a note on my naming conventions. If you see a driver that I wrote that has a suffix on it that's _EZ, that means it's a spin-based driver. In this case, we're also going to have _P2. That's going to be inline PASM2. And then _SP is for Smartpins. Now, I'm not suggesting you need to keep all three of these in your library. You can choose one and get rid of the suffix and throw away the others because they all operate the same way. I just provided them today so that you could compare, you know, kind of a Rosetta Stone approach. So if you're really comfortable with spin, you can then look at what we did with the assembly code and see, oh, okay, that's how that's happening. Now, there is a big difference, of course, with the Smartpins, but if you know what's going on with the spin and PASM code, and then you look at the Smartpins, and you will need to look at the Smartpins documentation, there is a bit of involvement with the Smartpins, but once you get used to that, they can be very, very useful, and this is one of those cases. So you'll see all three of those today. So here's the driver for the MAX7219. This section defines those registers we were just talking about. Sorry, it's these. These are the ones we're primarily going to concern ourselves with because we want to write things to that. And one of the things that I'll say that I do with the MAX7219 is I use it in what I call raw mode. There is logic built into the device that if you set a column to decode mode, then if you send it a 1, it'll display a 1. If you send it a 2, it'll display a 2. There's an advantage to that. If you're just doing numbers, then it makes it a little bit straightforward. But I find that more problematic than problem solving. So I use it in raw mode. So you'll notice in the code, as you get down to the bottom, I have built-in character maps for all the digits, the uppercase that look proper, the lowercase that you can pull off, you know, like a lowercase c or lowercase o or lowercase n. You can't do all letters. That is the disadvantage with 7-segment displays. But the ones you can, I have maps for, and I have methods to make it really easy to write any letter or any digit that it can display to any position. So I bypass the internal logic of the decoding and just use it as a raw device. I find it makes it simpler. This register is what allows you to set which columns use decoding and which don't. I set it to 0 because I want everything to be raw. The brightness register is probably one that you will want to use to change. I tend to keep my home dim. I have sensitive eyes, so I tend to turn things down. This register will let you brighten it up. And in fact, you can even use that for effects. I was telling Ken a story earlier that my friend John, again, I mentioned him many times, he and I did a project for the Army some years ago that was a paratrooper training device. So they had a mock aircraft and they were learning how to do these timing drills to get out of the plane. And we were using a big digital display with the MAX7219 driving it. And there were cases where they wanted the display to flash brighter. Well, we were able to do that using this brightness register and animate the brightness of the display. So that worked out kind of nicely. In the driver, we have 3 pins. We have a clock, we have data out or MOSI, and we have a chip select or our slave select. There's those 3 pins. We're not getting anything back from the MAX7219, so we don't have a MISO or a SDI serial data in pin. In the spin version, we're just going to assign the pins. And here's where I'm saving them. So this is coming from here to here. And here we're going to set up the pins for operation. I always start, even though it's not normally the first in the list, I always start by deselecting the device. So you'll notice it's pin high on the chip select or slave select in order to disable it. And then because this is a mode 0 SPI device, the clock and the data lines I'm presetting to low. Here is my normal setup. So out is a method that you'll see in just a second that lets you write to this register, this value. And so you'll need to look into the documentation, which is included in the download. So if you downloaded that zip file, inside the Tech Docs folder is the MAX7219 documentation. So you don't have to hunt for it. You already have it if you did the download today. Anyway, excuse me, you'll need to look at the register values that are allowed. So for example, I'll tell you, even though the code handles it, the brightness register goes from 0, which is the dimmest value that's displayed, to 15, which is the brightest value. So you have 16 levels of brightness in there. I'm not going to go line by line through this code because I don't want to deny you the opportunity to explore it, but you'll see that we enable the code and then away we go. What I've done in the, let's go to the out, because that's where the work is. Can I move this? Here is the working code. This is what is transmitting data to the device. It's called out. So R is a register number within the device, and this is the value to it. Now, this value bits is my workspace that I'm going to be transmitting out. The MAX7219 gets its data MSB first. So we go bit 7, 6, 5, 4, 3, 2, 1. And we're going to do that with 2 bytes. So since it's so nice and easy in the Propeller, I just stuff the register value into byte 3 of bits. So that's the leftmost byte. And then the value right behind that. Now, if it's a decode register, which allows me to change whether I want to have the internal decoding versus the raw mode, I actually save that so that I can deal with it later if I need to. And if it is a column or a digit that we can display, that's what these registers are. Digit 0, which is the rightmost in the display, and digit 7, which is the leftmost, then I'm going to save it to a segments buffer. The reason for that is I may want to, for example, have numbers and then turn on the decimal point or turn off the decimal point. So I need to save my values in a buffer so I can individually manipulate elements and then put them back. Here is the SPI code, believe it or not, this tiny little loop. So you saw in the SPI transactions, remember we start by taking the chip select low. And then in this case, since it's mode 0, the device that is writing to the bus puts the bit out there first. So we start by putting out on the data out pin, the MSB. So this is a little tricky to explain, but what it's doing is ROLs rotate left. It takes bit 31 and it rotates it around to bit 0. And then I write that to this pin. Yes, Carol? You're muted, Carol.
I didn't say anything.
Oh, I'm sorry. I saw you raise your hand. I thought you were trying to get my attention. Forgive me.
No, I was putting my work lamp up.
Oh, okay. Sorry about that.
I'm kind of working on something while I'm listening to you.
I understand. The reason I do it this way, because there are many ways to do things, is that it's doing two things at once. It's getting a bit into position and it's writing it out all in one line of code. Another way that we could have done this is this. I'll comment that out. We could have said pin write bits, oh, sorry, SDO, because that's where it's going, bits 31. Now, that writes it out, but we have to position the next bit, oh, not pinned, right? And then we'd have to say bits, left shift. All right. So this does in one line of code what I would normally do in two. Again, it's a style matter. Either way works just fine. All right.
Yeah, John.
Yes.
I think what could be pointed out is that the pin right, because you're only talking about one pin SDO, it's only going to look at the LSB of the second term. It's only looking at the LSB.
Yes.
That's why that works.
This is defining one pin. Yes, because, you know, in fact, I have parentheses here. I may have actually had this at one time and then realized I didn't need it, you know, masking off everything except the LSB. But since this is defined, as Chip was just pointing out, SDO is defined as one pin. It's only going to write the LSB of whatever the value is in this field.
John, I have a question. This is really a bit banged
Yes,
SPI. And
yes, it is.
what is the rate at which this occurs? And how do we know the device it's talking to can speak as fast?
That's a great point. So in the nice thing about SPI is it's really fast. I run at 200 megahertz. That's just my choice. The Propeller 2 will run faster. I did tests and this code runs about 600 kilohertz with this little loop. If you look at the data sheet, remember you always should do that, for the MAX7219, it claims it'll go 10 megahertz. So we're not even at 1 megahertz. Now, even if we bumped up to 300 megahertz on the for the P2, that would give us about 900-ish, you know, kilohertz SPI. So we're still under 1 megahertz. So with spin, we generally don't have to worry about overrunning speed. But again, that's a really great question because as I continue to harp on, you need to look at the data sheet to make sure it's going to be okay. I did, and therefore I know that this will work without any problems in spin. When we look at the assembly and the Smartpins code, we're actually going to tell it what speed to operate so that we don't violate the device. We don't do that in spin. So this is one of the disadvantages of spin. Precise control over timing is a little trickier to do. We could slow this down. The only way to speed it up is to increase our overall clock speed. And then we could slow it down by adding in, if we wanted to extend this pulse, for example, we could always add in like a wait US one here, and then we could do it here too.
That helps. I understand. Thanks a lot.
Yeah. So we can slow it down. Once 16 bits are shifted out, which again, remember, it's the register we want to talk to and its value, then we take the chip select high. That's when the value is actually loaded into the MAX7219, when we take the chip select back high. And this is just my habit. It's not necessary. Anytime I'm done with a SPI transaction, I just make sure that the data output line, the MOSI line rather, is low. You don't have to, it's just my habit. But that, I just want to show you this. In fact, we can get rid of this. These technically 5 lines of code, 3 are within a loop. That's how easy doing SPI output is. And you can adopt this to a large number of devices. Those 75 595s that I was talking about earlier, same code to operate
John,
on.
another comment for you, John.
Yes, sir.
This is all looking excellent. Another reason why you might want to think about driving SDO low as you do, when you're looking at things with an analyzer, your waveforms will look a lot cleaner. The start of every waveform will always be the same. So it's good practice when you're trying to find things visually.
Okay, thank you.
Mm-hmm.
All right, so this is the working code. So you'll notice almost everything else is going to be calling the out method. You can, this is a public method, so if you want to do something special with the device, the object will let you do that. This is exposed to the application. Now, with this particular version of the program, let me get back on. You'll see I've added lots of niceties over my old program. So, for example, clear. I have this in almost every display type program. It just shuts off, it turns off everything in the display. Here's the brightness control. Fill allows me to fill up all of those digits with a specific pattern. Put C is put a character C in this column. String is just like the string feature that we use inside of our terminal serial devices. And, it's a very common naming convention we use. Now, with the string function, we need to tell it the starting column, give it a pointer to our string, and how many characters we want to print. We do that so that we can do substrings. And you'll notice here that it will, if you put a length of 0, it will calculate the proper length for you and make sure that you can't overrun the display. And within that, you'll see that it's calling this method called char map or character map to take your character and turn it into the 7 segment bits that are necessary to display it on the LCD, or sorry, on the LED. You don't need to think about that, but there it is. The decimal function is a little bit involved, but works out nicely, as Ken found out today, right, Ken? Again, with everything else, you're going to tell it what column that you want to start printing in, the value you want to print. The digits, I really should have called this field. It's not how many digits will be displayed. It's the maximum number of digits you'll occupy in the display. So for example, I did a little test for Ken earlier because he was wanting to display temperature. And I said, okay, print out 723 with a single decimal point, but use 4 digits. So it had a leading space or a blank, and then 723 with the decimal point in the right place. And that's what this tells you. The decimal point says, hey, how many digits in this value come after the decimal point? So if it's 0, we're not using a decimal point. So this does, if you've looked at the code inside like full duplex serial, you'll see similar stuff to this. I won't go through it all, but this takes care of dividing down the digits and extracting the individual digits we need and putting them in the display. It also takes care, if you have a negative value, it will put a dash in front of it so that you know it is negative. So that works out nicely. Same thing for hex. Now, and binary, you saw in that display, there were hex and binary counters. You can also, I've used this a couple of times for specialty things where I'm doing specialty kind of animations. You can just put a bunch of raw data into your application and blast it into the display. That's what write buff does. Set DP allows you to turn on a decimal point or turn it off. That's what the state does. And here's how, you remember I was saying earlier that whenever we write to one of the digits that I save it into an internal buffer. Well, this helps us here because I'm able to either add the decimal point to that to the buffer and then redisplay it, or, you know, turn it off. So that's why we have to save what we want to know what's on the display in memory so that we can modify it and send it back out. Okay, so that's it. There's lots of, I've built up lots of characters, and you can see these constants that have all those. But for example, today, oh, I didn't save that code, Ken, but what I did for Ken, because he wanted to display temperature, is we wanted to have a little degrees symbol in the display. Well, if you look here, so this shows 7-segment mapping. If you've never seen that, there are 8 LEDs for each digit. There are 7 that form the digit or character, and then there's a decimal point digit. And so this is how the segments are organized. And this isn't specific to the MAX7219. This is how we deal with 7-segment displays. Now in the MAX7219, it wants the digits in this order. So the bit 7 of a value is the decimal point control, and then it goes A, B, C, D through G. For a degree symbol, we wanted A, B, F, and G lit. So I did something like this in the application. I said degsim equals %011 1 2. Yeah, so this is A and B and then F and G. And now I can write degree symbol to the display and I get this box displayed. Okay, so you can go through and create custom characters and do that. I've done all of the kind of normal things, and then there is a table here. This is so that you can do the strings and numbers functions. You'll notice that a lot of them are marked blank because the 7-segment display is limited, and we can't display every character in the ASCII set with that limited configuration. So what can be displayed, or what I think is viable for display, is there. You can, I've seen some people have made other decisions and have more characters, but for me, from a readability standpoint, I've done this from a, just if you're looking at this and wonder why I do things the way I do, if a letter like C can have an upper and lowercase value, then the uppercase is 1 and the lowercase is 2. All right. So the MAX7219 has been around for ages and ages. It's super cheap now. It once wasn't, and it's a useful device for adding really simple displays.
I think the chips used to be like $7 or $8 when they made a dip version.
They were. I think they were more than that way back when we first.
$12, yeah.
Stampworks, we had a MAX7219 in it, and it was really expensive. And then we selected another driver, but now we get whole fabricated displays for less than what the chip used to cost. Okay. In going back to that, you saw the code that Ken had run. Here I'm using a data table to create. Here's a string. This is the way I'm scrolling on the string that you may remember it said Propeller 2. And here's that example where we can't do an uppercase R with a 7-segment display, so the R's are lowercase. So it looks a little funky, but it's still readable. And the I'm padding it. You probably remember 32 is a space. So I'm putting 8 spaces, what I want to display, and then 8 more spaces. What that does is it gives me a clean entry. My string goes through, and then I get a clean exit because I'm filling the display with spaces. So if we look down in the scrolling routine, you can see it's really simple. There's not a lot to it. I'm going to grab that string size, and I'm going to subtract 8 spaces. I don't want to go all the way to the end because we want those last 8 spaces to stay there. So that's why I'm subtracting 8. So this, if you wanted to go in and change this part to something longer or shorter and rerun the program, it would just work. Leave the leading and trailing spaces on there so you get clean entry and exit. But this goes through everything but the last part. So here's where we're using that string function. We're starting in the leftmost column, that's digit 7. And we're saying display this string and give me 8 characters. And the delay lets me control how fast I want the scrolling to happen. And then we bump where we're starting inside the string. So we initially pass it the address from our data table, and then through the routine, we're incrementing that address. And what that does is cause the pointer to advance through, and that gives us the shifting motion. So really, really simple code, but gives a nice little effect. We've only got 8 characters on there, but you could have quite a long message as long as you had the characters available, scroll through it. This is how scrolling things work. The demo, the decimal demo is doing a 10-second countdown timer. Again, this is a thing you may have seen from me in the past, but I'll point it out right here. I want this to count down from 10 to 0 in 1/10 second units. So to do 10 seconds in 1/10 units, I need 100 units. So this 100, I put an underscore there to indicate, hey, those are tenths that follow after. But same kind of thing. I start and I hold the time, and then you saw it will again use a loop, and it will just decrement from 10 down to 0. And we're using the decimal display that is displaying that time using 3 digits. And we've got 1 digit that follows the decimal point. So that's why when you saw on the display, it said 10.0 to start with, because I'm telling it to put that decimal point right there. Okay. And the rest are just as easy. This one took a couple of minutes to write, but was kind of fun to figure out. I'm generating a random number and then manually turning it into a string. The reason that I do that is so that as we're incrementing through, I want it to start out and run for a couple of seconds, and then every second start solving a digit. And what that's doing is I'm not randomizing that solution. I'm telling it this order is telling me which columns get solved in which order. And every time we're on a new second, what I'm doing is I'm going through and I'm putting the final value, which is this one here, which is Parallax's toll-free number, and putting it into the work output, which is what I'm displaying. And then I'm I'm putting it out as a string. So very easy. So again, you could, if you were building an escape room puzzle, Carol, you could use this to create a rolling techie display. All right. So we'll just now show the differences in SPI code. So now you know how to use. I'd like to think you could happily use the 7219. This version of the program, which is marked P2,
John,
yes.
excuse me, I got a question on the last your demo A.
Yeah.
What's the reason with byte 0 in the DAT block for message? It's after your 32.8 spacing. It's in the DAT block right there. Yeah, that byte 0.
Yeah, because this is a Z string.
Z string, okay.
And so what happens is when we get out to this point, if it's just to prevent a runaway situation. It's probably not actually needed in this code, but I tend to be protective of things. If I'm doing anything with strings, even if I know I'm going to be using substrings, I throw the 0 terminator in there anyway.
Okay. All right, great. Thanks.
Overprotectiveness on my part, probably.
Yep.
Okay, so the next version, again, every bit of code is the same as what you've just seen, other than a tiny bit of code in the driver. Now, the other thing too is you'll notice the setup for the assembly code, since we can control the speed at which assembly runs or the signals we're creating, we're going to pass it the clock speed that we want to use. So that's a slight difference. We're doing the same kind of setup with the pins because we're bit banging this. And then we're going to create a timer that is for a 1/4 clock cycle. You'll see that in just a second. So the only differences are this small bit of setup here, and then in the out method. So what I've done is replace that 6 or 7 lines of assembly with this bit of, of spin with this bit of assembly. And now it looks a little scary perhaps to those who haven't done any assembly, but I can assure you this is really straightforward stuff. And if you're not, interested in assembly now, when you are later, then you can compare the two, and you'll see that one of the things that Chip has done with Propeller assembly is made it really functionally useful. It's a lot of assembly languages, and not that I know a lot, but as I look at them, they're very disturbing for my simple mind. The Propeller assembly is really very clean, and the P2 is amazing because you can do so many things with so few instructions. So you'll see the same process, but now it's happening at the assembly level, so it's very fast. Drive low, DRVL, that's the same thing as pin low. And there's my pin, my chip select pin. Now, this NOP or no op is just giving it a couple of extra cycles to let that pin go low so it alerts the device. One of the really neat things about PASM 2 is it has a repeat structure in it, just like spin does. So what this line is telling us is that we're going to repeat the next 8 instructions 16 times. And you can, of course, have variable. Well, you can have a variable here. I don't know that that'd be wise to have it here, or if you even can. But in this case, we know we're sending 16 bits. So that's what we're doing. Now, this is doing the equivalent of that rotate. Before I've set up the bits just the same as before. So my first bit is in bit 31. And when I do a shift left, that will push it off the end, but I'm capturing it in the carry flag. That's a flag that's inside the register. And then drive C says, hey, take whatever is in the carry flag and write it as an active output to this pin, the data pin. So then I'm going to wait ticks. Remember, I probably didn't cover this as well as I should have, so I'll go back over that. Ticks is the number of system clock ticks for our frequency, our system clock frequency, in 1/4 of a clock cycle. Because what I want to do is I want to drive my data out, and then I want to wait a little bit just to make sure everything's settled before I take the clock high.
Hey, John, maybe good to specify 1/4 of a SPI bit cycle or SPI clock cycle.
Okay. Oh, that I see what you're saying. That'll make, I'll put that in the comments before and re-release it. So yeah, so it's 1/4 of a SPI clock cycle, not a Propeller clock cycle. Thank you. And now we take the clock pin high. Now we have 2/4, so that's doing our high pulse on our clock line. We drive the clock low, and then we're going to wait another 1/4 SPI clock cycle and do the whole thing over again. The difference between this, I mean, it's a few more lines of code, but now we have more precise timing. Whereas with the spin version, we're going to be dependent on the clock frequency setting for the project. Since the ticks value is derived from that, this will run at the same speed regardless of what we have our Propeller clock set to. So, and in the end, same thing, drive the chip select pin high, and then as I was saying before, I leave my data pin low. It's the same thing, just doing it faster and more precisely. Oops, I had to cough and I thought I could mute myself. Okay. Questions on that?
The Zen height.
Oh, thank you.
Do you have like a scope picture or anything of it running?
The data capture that I showed was from this assembly code.
Oh, okay.
So I can go back to that. And so you can see that this is, boy, let me zoom in here. So you can see from here to here is 10 microseconds. So this is running, I think I was doing 5 megahertz here. It's not really fast, but faster certainly than we can do in spin. Okay.
John?
Yes.
How does ticks get its value, or is that something in Prop Tool, or?
No, I'm sorry. I went through that really quickly. I'll go back. In the start method is where we're configuring everything. What we're doing is we're taking the clock frequency from our system. We're going to specify our clock speed in kilohertz. And so I multiply that by 1,000 to get megahertz, and then divide that into the clock speed. And that will give us how many ticks we have in one SPI clock period. I'm now going to divide that by 4 by shifting it right 2 times. And then I probably actually need to change this to 8. Technically, because each wait tick, a wait X instruction, adds 2 clock cycles. It's not going to hurt anything even if you have nothing in there. But that's where ticks is being calculated. Now these are my global variables here. When we do inline assembly, we can't use global variables. So what we do is, you'll notice this instruction right there. I have copies of my pins and my ticks value locally. So this copies my globals to the method, because when the interpreter pulls the method into the cog to be executed, it will pull over all of these values. And so I have these to run in the cog. So it is one of the little details to understand about running inline assembly, but it's pretty easy to do. So, you know, this is all being shuttled over into the cog and running at cog speed. Okay. Any other questions? Again, easy stuff, and I've gone past my time. Okay, final version. This is the Smartpins version. Excuse me. And again, I'm going to encourage you to spend a little bit of time with the Smartpins documentation. It'll take a couple of reads, but it's worth the time to do it. So here is the startup. It looks the same as the assembly in that we're passing the pins and a clock speed. But in this case, we're setting the clock pin as a pulse output. It's one of these Smartpin modes. And what we're going to do is the low word of the X register in the Smartpin. You'll remember, I think I mentioned this before, but Smartpins have X and Y registers that we put data into. And if we're getting something back from the Smartpin, it comes from its Z register. So the X register, the low word gets the ticks in our SPI clock period. So you'll see this looks the same as what we had just done. We're converting this to megahertz and we're dividing it down. Now, here is a caveat. Because we're using a 16-bit value, this has to fit into 16 bits. So you probably won't run into many problems with this, but if you're using the pulse mode with very, very, long pulses, you may run into some trouble because of this 16-bit limit. So it's something to look at. There are more than one ways to solve the problem, but for clock speeds like we're doing here, it's not an issue. And this is just one way to do it. If you happen to look inside the loader code that Chip wrote for the Propeller, He uses a different mechanism for generating the clock. Both work because we're dealing with transitions. I like the pulse mode because I can say I want this many clock cycles and that's what I get. If you're using transitions mode, which I think is what Chip uses, he has to double the number of transitions he's sending out. You know, so if he wants 16 clock pulses, he says, give me 32 transitions. So you get, you know, 2 transitions for each clock. Both work. I just prefer this stylistically. So the low word of X is the length of my clock period. The high word is the high side of that period or my clock pulse. So I'm just taking this value and I'm dividing it by 2. So I get a 50% duty cycle. That's why you saw that clock looks the way it looks. And then we use pin start to do that. So the mode I'm selecting is pulse. Now remember, with a smart pin, to have an output that is active, that is low or high, you have to enable it inside the smart pin specifically, because we're no longer using the direction bit as an output control thing. We're using that as a smart pin on and off thing. So if we want the pin to be outputting a signal, we need to tell it that that's okay by putting that this is the output enable for the pin. So my mode, my M value is pulse, and I'm ORing that with output enable and then setting it up, and then pin start sets it up. The Y register is here. Initially, I don't want any pulses going out, so I set that to 0. Doing the same thing with this sync TX, this is the synchronous transmit. This is the SPI output, if you will. It's also an output mode. Now, the way that this works is it needs to know where the clock pin is. So we're telling that if you look into the pins field, and I covered this last week, it gets a little detailed, but in the normal pin configuration, you can have A and B pins. You have to tell it where the clock pin is in relation to that data pin. This handles that and puts those bits into the right position. This is, I'm presetting this for 16 bits. And this is, and maybe I'm gonna ask Chip if he'll jump in the different modes. Where in this, it's called start-stop mode, and I'm not sure I understand the difference between that and the other modes. I know this works.
I was just reviewing that when we were talking about it 15 minutes ago, and I don't really understand it. I got to go back and read that thing really carefully.
Okay, this works. This code works. The thing to note, it's a little interesting, is that the value we're going to put here, which is going to fill these 5 bits, you have to, these are your number of bits, and you need to subtract 1 from it, because in a 5-bit field, you can have 0 to 31, which would give us the whole 32 bits if we were going to shift out a long. So in this case, I'm starting the pin, same thing with data initially, and then I'm immediately turning it back off because I want to reset it. I don't want anything happening on that pin. So these take a little bit of time to understand. I'm not going to lie to you, but once you've seen this example and you've gone through the Smartpin documentation, it'll start to make sense. I'm using Smartpins more frequently now. And so that gives us the ability to now talk to the pin. So we're going to go back. We're going to do like we did before. We're going to go to this out method. And you look, it's a tiny bit of code, actually, because we're using the Smartpins to generate everything. Now, I've got a note in here that's important. The MAX7219 shifts out data MSB first. But Smartpins always want to send data out the other direction, LSB first. So what that means is we've got to flip the data around. There is a instruction called reverse that does that. Now, because I was already presetting to the MSB end of the value, all I had to do is reverse those bits. So I'm reversing. This is saying, hey, flip everything from bit 31 over to bit 0 and vice versa. If you have shorter values, then you'll need to change that. All right, but here we go. As always, check the chip select low. Now what we're going to do is we're going to write our output bits to the data pin. And then we're going to re-enable the pin by setting the direction bit to 1. Now here's where the magic happens. The clock pin is active. We started it up and we didn't do anything with it. All we have to do is say, hey, give me 16 clock pulses. What will happen now is the clock pin will start generating those clock pulses. The data pin, which has been linked to this, will automatically put the bits out where it needs to go. So they're synchronized together because of our setup. Now, we don't want to wait around forever, and we can't look at the pin as a normal input anymore, but the pin will tell us when it's done. So we can use pin read on the clock, and when that goes high, it says, okay, I've shifted out all of the bits. So once that's happened, we reset the data pin so we don't get any shenanigans out of that, and we take the chip select back high. There's a lot going on here, but it's saving us a bunch of coding, and this is all happening at very high speed. So we can make the data stream out of a Smartpin very, very fast because it's all happening at a logic level. It's not even, it can be, technically it could be faster than assembly because it's happening at a gate level versus assembly. There are still instructions and instruction overhead in there. I'm expecting to see people's heads exploding like a Scanners victim from that movie Scanners.
Well, John, I could show an example now if you want to take a break.
Oh yeah, please. That would help because I need, it's getting tired.
Stop in your screen share. So I called up JonnyMac today at lunchtime and he said something about putting the humidity sensor together, the CM2302 with the, is my screen shared by the way?
Yes.
Okay, I don't know why that's always so hard to know what other people are looking at, but anyway, he said, well, maybe you can get this working, and I couldn't get it working with the old object because it didn't have all the methods I needed, but he added one that made this quite easy. So I took the code that is published as a quick byte for the CM2302 DHT22 sensor, humidity and temp, and then I extracted what I needed out of it, and I made a program that integrates the two. And John, maybe you want to comment on when we use your code, how we attribute the proper way. So I just said this is JonnyMac's code with a bunch of edits by Ken.
Yeah, I with respect, I'd rather you say it's written by you based on code written by me.
Because once I've messed it up, it's you don't want your name on it.
I don't want to be responsible for your great work.
Thanks. I took your email off, so no one's going to be contacting you. So I added the sensor here on pin 16, and then John made the degree symbol. I put that in, and all I had to do was start up the humidity and temperature object, which is down here in the setup. And John can tell me if I did all this, in the proper way or not, but I started it, so now it's running, and now all those values are available anytime I want them, so I can just retrieve them in this main loop. So I first take the temperature, the Fahrenheit, and I put it in a variable called tempf that I declared locally, and then I also made temperature for Celsius and then relative humidity. And then I did a little messing around with where to display it, and it came out quite nice. And it is that cold in my room, and this is the same sensor that I dumped in the water the other day that made everybody nervous. But I'll blow on it. Saw the humidity go up.
Yeah. Hit it with a blowtorch like you did the other day.
All the fires in my other office in heat. Anyway, it was really nice to take one object. I don't know if there's a degree, if I'm supposed to use a degree symbol for centigrade. I forgot what's proper.
I think that's correct. You Yeah, because it's degrees. It's just a different scale. Oh, yeah, you should put a degree symbol in with the centigrade as well.
Okay, I'll add that back in.
That way we know what that, yeah, the two of them combined tell us its temperature.
But I just want everyone to know it's really pretty easy to take one object and then combine it with another and do things the way these demos are written.
Yeah,
So
that's a good real world example right there.
yeah, it's pretty simple. So here I'll just recompile it and I'll add in the, let's see if I got it right. There it is.
Yeah. The important thing, especially for those that are new, is even if this is just an exercise, the exercise will help you get better. It's practice. You know, every day, little projects like this will, you know, get you to that point when you're in a scramble and say, oh, now I have to do something serious. You'll have had the time in. So you know, every day I'm doing little bits of experimenting because I got noticed from my friends at the laser tag company the other day, oh yeah, you know, in 6 months we want to do P2 laser tag. That's not a lot of time for a project that big. Luckily, I anticipated this and I've been experimenting, so I've got a little bit of a head start. But you know, it's better to be practicing and having, and later, you know, you may use the code or learn something from the code that applies to another project. The key is to just play, have fun.
Hey, John.
No stress. Chip, did you say something?
Yeah, so I've been looking at the dock again, and basically there's a continuous mode and a start-stop mode. The continuous mode is what you prime when the smart pin is still in a reset, and then it starts transmitting, and then you have that whole data frame to update another Y pin to put a new data word in. And the other mode is so that one will do like gapless transmission. You know, once you prime it, you can keep feeding it. As long as you meet the schedule, it'll just keep outputting contiguous bits with each clock. The other is called start-stop mode. Which is
what we're using.
Yeah, that's where when you write a value, the LSB is immediately output to the serial out pin.
Okay.
And you can also feed it with Y pin. But there's a reason, and I'm not really clear why I did it this way, but there's the start-stop mode is better and more convenient than if you're like doing things in bursts, not continuously.
Right, which is the case here. Now, you know, for example, in your loader code, you're using the streamer to just blast bits out to the flash nonstop. So maybe that's where the other mode is more.
Oh, I didn't even for that. I just used the streamer. That was to do that. I used a pin with like the clock cycle or transition mode output.
Yep.
And the streamer, because the streamer, see, what you have to do is you have to send this thing right Y pins, or through the synchronous input you read the pin. So there's some management involved, right? But once you get things queued up so that you can turn the streamer on, it'll just shoot it in and out of memory, you know, right to and from the I/O pins.
Okay. Well, it obviously works very fast. In fact, you'll you know, people that have played with, say, the P1 and the P2 notice how fast, even when you're saving the flash. Now, part of that has to do with the speed of SPI versus I2C. SPI is much, much faster. And then, as Chip was indicating, you know, with the streamer modes where you can rush out as fast as the device will take it. And that's what he's doing there. So since we're talking about the flash chip, let's play with that a bit.
Yeah, and one thing about the streamer versus the smart pin is that each cog only has one streamer. So you have to give it like really prime application.
Okay.
Right. Yeah. And then so if you have little things happening on interrupts, that's much more convenient to use smart pins for.
Okay. Yeah, because we can assign smart pins to any pin.
Wait, say that again?
We can have as many smart pins as we like.
Right, and they can generate interrupts, which can create the events that you feed or pick up. You feed new data to it in time for gapless transmission, or you receive the data before it overruns and then refills.
Okay. Cool. Well, let's look at, since we've been talking about the flash, let's talk to it, because the MAX7219 was just, we were sending data to it. We're not getting anything back. We can read from the flash, so we'll do that now. So, there we go. So there are, just as we did with the MAX7219, there are 3 versions of this program called Flash Reader. And there's a spin version, an assembly version, and a Smartpins version. I'll skip the assembly because it does the same thing as a spin. It's just an assembly. And we'll look at the object called the P2 Flash EZ. That's the spin version of the Flash Reader. And there is a lot to this chip, so I'm going to just kind of do a broad brush. When we start, because this is targeting the P2 flash and we know where the pins are, we don't have to pass anything to the start method because those pins are fixed in a P2 project. I wrote this object not as a general purpose flash object, but a P2 flash object to do the reading. Now there's lots of registers and lots of other stuff that you'll find. The documentation for the flash is also in your downloads, but you've seen enough of my code by now, most of you, that I have in my fixed pin space. Here's our programming pins, and here are the pins that we use for the flash connection. And you'll notice, we have chip select, clock, data out, which is MOSI, and data in, which is MISO. So here we're pre-configuring the pins. And then in this case, I've got 2 values that are, from the old basic stamp days, shift out and shift in. Now, we're going to shift MSB first, and we can shift any number of bits up to 32 with this method. So this rotate right, I should have done a graphic for this because it's a nice instruction. I'm so glad Chip added this to spin. You can do this in assembly, but it's really great that you can do it in spin. What it does is it takes your MSB and it puts it at bit 31. In the past, we would do things like this. Value equal to value. That would do the same thing. We want to shift over. If we have 8 bits, we want to shift it 24 spaces, bits over, so that the MSB is aligned with bit 31, because that's what we're going to shift out. This just is a little nicer way to do it, I think. It accomplishes the same thing. So again, we're aligning the MSB of our output with bit 31. And here we are. Look how this is the same code we saw before. Now, the chip select isn't in here because in this case with the flash, we're often sending data and getting data back all within the same chip select cycle. So the chip select happens outside of this. You'll notice too that I've made these private because we don't want the calling application to be doing direct shift in and shift out. We want to protect that. But the same thing, we grab a bit from the top, clock high, clock low, easy peasy. Shift in now, we didn't talk about that before, but now we can. It's the same kind of thing. Remember, this is a mode 0 device, so the data is available before the rising edge of the clock. So when we do a shift in, we're taking our result variable, which we've declared here. Remember, anytime a method in spin 2 is going to return a value, we must declare it, because unlike spin 1, spin 2 methods do not automatically return values. We have to tell it. So that's what we're doing here. And what we're going to do, this is coming in, again, the data is coming MSB first, which means we're going to shift it into the value from the LSB side. So visually, if you draw it out, you'll see where it makes sense. So what we do is the first line, this is doing 2 things at once. This section right here shifts whatever is in result over to the left by 1 bit, which makes bit 0 now free and clear for something new. And then we're going to OR that with pin read of that pin. And since this is just one pin, we're only going to get a 0 or 1 from this. So that's how we pull in the bit. And then we generate a clock pulse, and we do that for the number of bits in the value. This is, so you can see, again, this is SPI in spin. It's very, very easy to do. And since the P2 runs very fast, if this is all you ever want to do, and you're just doing small amounts of data, you'll probably never notice any kind of delays. So if we look at a couple of things, again, the flash chip is a little bit involved. One of the neat things about it, though, that is useful for some applications, in fact, we're going to be using it in the laser tag, is the flash, like a one-wire device, has an internal 64-bit serial number that's unique to every chip. This method will give us that. Now, we're going to return it as two 32-bit values. So you can see, again, this is new to spin 2. We can return 2 values, and I have a high long and a low long. So here's the whole transaction. We're going to take the chip select low. We're going to shift out this command 4B, and we're 8 bits of 4B. This tells us that we want to read that unique ID. And if you look in the data sheet for the flash, it says that after that command, it wants 32 dummy bits. So we just send out 0 32 times. That's, again, this is a requirement from the data sheet. It's not something I made up. And now we can do 2 32-bit shifts to retrieve the serial number, and we're done. So you can see a lot of the transactions are built in this manner. Now, I made this specifically to read the flash chip. And so this is kind of at the heart of all of the reads. What we're going to do is we're going to pass it an address in the device that we want to read, how many bytes to read, and then an output array for that. So that's PDEST is a pointer to the destination. If you look at, you'll remember perhaps when I was talking about this, this transaction, this is a read transaction. These 32 bits are the read command, which is this 3, and then the address. So if we look again in the code, you can see this read data. If you look in the constants value, read data is 3. So that goes into byte 3, which is the upper byte of the address. And then we can shift out those 32 bits. Now the flash is ready to give us as many bytes as we want from it. So we are going to go in a repeat loop with a number of bytes, and we're going to read in 1 byte at a time and write it out to this destination. And then when that's done, this trailing plus plus, this post increment operator, will bump us to the next address of the destination. So this, we can read an arbitrary block of bytes. And when we're done, of course, we turn everything off by pulling the chip select high. So you'll notice, for example, all of these other reads call on that. That way, read is in kind of one unified place, and all of these others are just saying, so if I want to read an individual byte, I'm calling read block and telling, give me 1 byte and put it into my result, which I'm declaring B right there. I'm doing the same thing. 2 bytes is a word, 4 bytes is a long. There is a value inside the flash called a page, which is 256 bytes. That's what this is doing. And because pages are aligned on specific addresses, this actually manipulates the address first by making sure that it is on an even 256 byte boundary. The interesting thing about a page in the flash is that's the smallest chunk you can write to in the flash as a block if you want to do things quickly. Interestingly, though, with the flash, it's a little bit on the complicated side in that it has to be erased before it can be written to. And sadly, the smallest chunk in the flash that you can erase is 4K. So if you've ever wondered why the complication is involved in these SPI file systems and that, it's because they have to buffer these 4K chunks in and out of the device. So it gets a little bit involved, but let's just run this program because it will show us that we can talk to the flash. F10. This is one of those programs where you have to open the terminal and then press a key to get it to start. And so here it is. Here is the ID from my flash. This is the manufacturer code and the device type, which has to do with its size. There are a couple of different versions of this in here. This one, this is called the I don't know how it's pronounced. I'm calling it JEDEC, but it's JEDEC, it's JEDEC. It's information that tells us about the chip. And this is telling me that it's a 16 meg chip because one of the bytes that comes back from the JEDEC information is the size of the device. And then I have a little method in here that does a dump routine. This is based on stuff that Ray Roddick has done. He always has these nice dump routines to dump data. So I kind of copied what Ray is doing. So it's doing 16 bytes per line, and it's like an old school debug where it has the ASCII version. And you can see, if you get right here, you can see strings from the code. That's why I selected this device, because this is right at the end of the interpreter in the memory.
John, that's a question I wanted to ask too. Can you overwrite your program or cause trouble?
Not with this program.
Because
this program reader, but with the other program that is in there's a thing called Flash Explorer. It has the ability to write to the flash, and so I put a warning in there. Keep everything above address hex 100000, which is the 1 megabyte level. That way you'll never interfere with your code space.
Well, this is really handy then, because you could store a ton of data here.
Yes, with the writer. And yeah, so the Mike Green is working on a flash file system utility. And so that will be helpful. There was discussion yesterday about it as well. This is just, for simple stuff and to look at. Again, here, the nice thing about using the flash is we get a serial number for our devices. And again, with the laser tag company, they're actually very happy about that. They don't have to serialize them separately. In the P1 version of that project, there was an iteration of the board that had a 1-wire serial number on it because they wanted an electronic serial number. Later, it turned out we needed that IO pin so badly that we gave up the serial number, but with the P2, we don't have to because the flash has a serial number that we can use.
And could you comment again on the amount of space in the flash that you can read and write to?
Well, technically you can read anything and you can write to anything. You just, for the P1, for the P2, I'm saying, because again, I'm overly cautious, keep everything, if you want to do experiments with writing and that one program does that, keep that above the 1 megabyte point. Now, I know people are thinking, but wait, John, there's only 0.5 megabyte in the P2. Well, the P2 architecture is designed, though, to accommodate 1 megabyte. So after the P2 is dominating the world and Chip says, okay, I'm going to make a P3, we just habitually want to stay out of that space. Just keep it above 1 megabyte. It's easy to think about.
Clarify that a little further, John. 1 megabyte to where? To
the end. So here, this is showing me I have a 16 megabyte device. So I can write
15 megabytes?
No, it's 16. So you have 15 megabytes of free space you can play with in my world. It's a 16
That's a lot.
flash. Yeah, it's a ton. Remember on the Propeller 2, we would normally put a 64K EEPROM on there. Now we've got a 16 megabyte flash.
Yeah, I'm just thinking with Blockly, like we could write to a small number of cells in the EEPROM before we cause trouble. That was my only experience writing to the EEPROM.
Yeah, people get very worried about cell damage. I really think you'd have to do something, with an automated process constantly writing to a cell. I don't think with human experiments or reprogramming, you're ever going to damage the flash.
Yeah, I'm talking mostly about the limited space. that was
No, but
available.
yeah. Now you have, and there's nothing that would stop you from putting a 32 meg EEPROM on the board. I assume they're available. But...
Question?
Yes, sir.
You were talking about cell damages. Is that the term that they keep referring to on the forum when they talk about leveling?
Yes.
Is there like a technique to write to different locations?
Chip can probably explain it better than I can.
Yeah, you just want to spread your write activity around evenly so that you're erasing and reprogramming everything at the same frequency. So this is where like journaling file systems come in, where you actually just have this additive process where you keep rolling through the whole 16 megabytes, and you know where you can write a new record. So you write that record, cancel out the old one, and then periodically you have to do some erasures in order to free up some space. But that inherently wear levels, right? Because you're traveling around in a big loop. And there's also some safety in that, because if the power were to go out at some point, you're only like 1 delta bit away from you can figure out where you failed and then go from there. So it's kind of, there's some fault tolerance in that sort of system too. But you have to wear level, because if you just like kept your file allocation table in the same place and kept erasing and reprogramming and erasing and reprogramming, that's going to fail far earlier than the rest of the chip. So you want to do some technique where you keep looping around the entire memory, erasing and rewriting, and that will wear level. Because you get about, I think they guarantee 100,000 erase program cycles, you know, per bit.
There's an object I wrote that's in the P1 library called WinBond that does some of this. It sets up a file system with eight and 3 file names, and it does some simple wear leveling by randomizing where it looks for the next available block. Anyway, take a look at it. I'm in the process of making sure it works right with John's low-level code, and you know, maybe next week I'll have it posted.
Copy that, thanks.
I have a question.
Sure.
So you have 16 megabytes. Let's say I buy a new Propeller board and it's got this flash on it. What's in that when I get the board? Is there any code in there at all, or is that purely for user program storage?
Well, there may be some production test code, but you can overwrite that really quickly. So the current P2 has a 0.5 megabyte RAM space that we're going to load from the flash. So of that 16 meg flash that is, you know, presented on current P2 boards, 1/2 of it is going to be for your program space. 1/2 a megabyte rather is for technically 15.5 megabytes. You can do anything you want with. Now, again, I know that the architecture is designed for one. So if there's ever a free, I'm just keeping all of my stuff. I'm just making my personal decision to, in the flash, write starting with 1 megabyte and higher for application data, not program space. So for example, the laser tag stuff that I'm going to be doing, we'll store all of the user configuration stuff above the 1 megabyte location. That way, if we download a new version of the code, the user data is not blasted out. It's available for the next version of the application. Does that make sense?
Yeah, and I'm just curious, how do you tell it to load your code somewhere other than at the beginning of that flash? Does this spin tool let you do that? Let you select where you're going to program?
No, your application is always going to start at the beginning. We don't anticipate we're going to be downloading a program 100,000 times. User data, though, could be changing a lot, especially in a data a data collecting type situation. So that's where you're more concerned about the wear level.
Yeah, we just don't do anything with the memory above 512K because that's as big as your app can ever be that we might download. So the memory beyond that, we never touch. It's there. You would need like a file system in the form of an object to access it.
Yeah, so the code that I've been working on is kind of the low-level code that is in Spin, so it's very easy. And then what Mike, who was speaking a moment ago, is creating is a file system on top of that that will allow you to read and write files and do some basic wear leveling. And it is dealing with the hardware part of the flash through code like mine. So there's, this is kind of a system. I don't know. It's, this is a hardware level code, and then what Mike is writing is kind of a system level thing, and then your application would call that. So it's a very layered approach, like you would have in an operating system. You have a device driver, and then an API, and then your application's going through the API.
Yeah, having a good file system that is in the form of an object is key to being able to do all kinds of stuff in the future.
Yeah.
Even building an operating system.
So I had on the Propeller 1 hooked up an SD card at one point, and there was a FAT library that I used to be able to store things onto the SD card. So that you're talking doing a similar thing, but doing it to this flash memory.
Yes, in fact, Ray Allen, who's one of the forum members, he took FSRW, which is one of the file systems that people use on the P1. It's the only one I use. Kai as another system, another guy wrote one. There's a few, but Ray took FSRW and made it work with the P2 flash. So he was treating the P2 flash like an SD card. Now, the difference, though, there, I believe, is that he can't control, perhaps wear leveling stuff. Where remember, an SD card is a smart device. There's intelligence inside the SD card that is taking care of all that wear leveling stuff for us. So this is where what Chip was talking about is having a file system object that will do that is important. And Chip, I know, has something in mind. There's a guy down in Australia named Brian who is part of the project for using MicroPython on the P2. He's got a file system that he's working on. So there are efforts in these ways, something that we do need in the P2 community so that we can use all of that data. We have a data storage space available, in a simple, practical way.
Yeah, having that little 8-pin flash on there is very nice. That thing is 16 megabytes. That's as big as hard drives used to be.
Yeah.
And for the scale of what is going to go on with the P2, it's like a hard drive. And
yeah,
the component is cheap. It's like, what do we pay for those things, Ken? Are they like 80 cents or something or less?
I don't have it in front of me.
I just used one on a P1 project because the client wanted to store, motion control data, and it was far more than we could fit in an EEPROM, even stacking EEPROMs. So we used the flash. So I wrote a really simplistic thing there, since we know that they're not going to be reprogramming the device very often, and they only have 10 animation things they want to do. In that case, one of the chunks of data that you can deal with as far from an erase cycle in the flash is 64K. So I assigned 64K blocks to each program, and when they want to update their program, which again is going to be very infrequent, it just erases that 64K, and then they have that much space to record into. So let's look at I'll skip ahead to the final program because it shows how to do. Oh no, I take it back. I really wish this banner on the top would get out of the way of my ability to see my. Okay, so here's the flash reader code that we were just looking at. Doggone it. with Smartpins. Yeah, because with Smartpins, we have data in and out. So we're going to set up 3 Smartpins for this because we have to, so we saw this before. So here's our clock. We're using pulse mode. Here is our MOSI, our data out. So that's using the synchronous transmit mode. And then there is a synchronous receive mode. And you'll notice, again, the synchronous receive needs to be aligned with the clock. So you'll see that's happening here. What happens inside those bits, I covered this once before, so I'll go very quickly here, is that we don't put the absolute pin number into the field. We put an offset from where we are. That's why we're doing this subtraction here. And then it's in the upper right of the word. That's why we shift it 24 bits. But so this gives us the offset to the clock. We're doing the same thing here. This is our clock pin. So if we look now in our, here's our shift in and shift out with Smartpins in assembly. As I said before, we have to be able to flip the bits around for the Smartpin because it wants to shift things out LSB first. Now in this case, we have a variable bit number of bits. So what I'm doing is using this rotate right to get the MSB of our value into bit 31. That way I can flip it very easily here. Now, some people, I could probably just flip the byte here, but I did this deliberately so it matches more closely with the assembly code, and I tend to do that. So there will be times, I will admit, I do things in a slightly non-optimal way if I'm doing multiple versions of the code so I can compare them. The point of all of this is that we need to get our MSB bit, our value, flipped around so that it's going out the LSB end. That's what we're doing here. So this is setting up our write. This kept me up till 5 o'clock in the morning. I forgot that line. So it's really critical that when we're doing a write and we have variable bits, we have to update that. I had left this line of code out, and I think I told Ken this story. It was a Friday night going into Saturday morning, and I said, I'm not going to bed until I get this code working. 5 o'clock in the morning, I finally remembered I had to put that in, and it got it to work. So I should have just said, hey, I'll figure it out in the morning and went to bed. But anyway, here we're loading up the number of bits. That goes into the X register. The Y register gets our value, and then we're enabling, remember, we're turning that transmit pin back on, and then we send out the bits, and away we go. So this is like you saw before. The difference is we have variable number of bits. Inside the MAX7219, we're always sending 16 bits, so we didn't have this line. Shift in works similarly in that we're going to reset it first by turning the shift in pin off by taking its direction pin, floating it. What that does is that resets the internal value. This is critical as well because you don't want any garbage left inside your holding register when new stuff is coming in. So we reset that here. We tell it how many bits are going to be coming in. And again, remember, it's going to be our actual number of bits minus 1 because it's going to populate this field. Now we activate that and start our clock. So this section is what gets our bits into the propeller. But it also comes in LSB first. So here we're going to grab the value out of the smart pin. So this is how we get a value from a smart pin, is with the read pin. This is different than pin read. This is read pin. This is giving us the Z register value from the smart pin. We're going to flip it over so that we fix the MSB. And then if there are fewer than 32 bits, this may not be necessary, but again, I tend to be very cautious. If there's less than 32 bits in our value, what this will do is zero extend. which is, it'll just fill from this point up to the MSB was 0. So we have a clean value that we return to the caller. But pretty straightforward. This goes, and remember, all of this can happen at very, very fast clock speeds, probably faster than we can practically do in assembly. So now we have shift in and shift out with Smartpins. So any device that you have that uses SPI, you can do it pretty straightforward. There's a little bit of setup code, but this code is not difficult to do. So this, if we ran this variant of the program, you'd not see any difference other than this screen would update a little faster because we're getting the data back a little faster. The final program that I prepared for our today, and this thing, oh, I can move that bar, that makes it nicer, is this thing called Flash Explorer. Now this, you know, danger, Will Robinson, danger, this could trash your application. It won't break anything, you'll just have to re-download again, because this program allows you to write to the flash. And that is happening with this object called JMP2 Flash. So this is a read-write thing. And because this is more for guys like, you know, Mike or Chip or other people that are going to write file system drivers, I do a combination effect here. So here's the same things that you saw before. So we're using Smartpins. But what I'm doing, again, in the spin environment to make things really fast is that, remember that block read that we did before? It was all 100% spin. Now I'm using inline assembly combined with Smartpins. So for a native spin application, which is what I'm going to call stuff that go through Propeller tool or Peanut, I'm going to call that native spin. If you're running FlexProp, it's going to get compiled to assembly. So it's not interpreted spin anymore. But for a native spin application, I think this gives us the best speed because we can do the block stuff. So I won't bore you with all of this because it does get a little thick. But if you look through this and look at the notes, you'll see these are the same things that we were doing in high level. We're just doing it in assembly. So this we can read or write as quickly as the device will allow. So if this program, I'll run the Explorer program. So again, be careful with addresses that you happen to use on here. In fact, you'll notice, I think I put a comment up here, you know, don't modify anything below the 1 megabyte point, you know, or if you do, you might be wondering what's happening. You could brick your application, but that technically you could use as a feature. If you have some kind of security in your application and you feel like that somebody stole your code and copied it somewhere else, you could just erase the flash and then it would be gone.
You could have fun and make self-modifying code and get yourself really confused.
There you go. Yeah, be very careful with this. So I'll run it so you can see this is now there's a couple of things happening here. I have a page buffer, which is a 256 byte RAM buffer. So this was giving me a start to some practice for a driver that would allow me to read in 256 bytes and modify it and then write it back out. Now, this really probably needs to be 4K because we can't erase anything less than 4K. But you can write a 256 byte block. So it might be feasible to read in a 4K buffer and then go through that in 256K or 256 byte chunks rather. And if you know that that chunk didn't get modified, then don't bother writing that block to the flash so that you save wear and tear. But here, I'll run this so you can see. This needs kind of a whitish screen. So this will look a little bit like the other, but then it will do some other things. So here's that same stuff we saw before, and now this is just a small chunk of the flash. Here was my RAM. Remember, the Propeller always clears any declared RAM variables. That's why we see that's clear. So then I read from the 1 megabyte point, and this was erased. So when the flash is erased, it will present as ones. So you see all FFFFFFs. That's it. That's an erased block. So what I did then is I went in the code, it goes in and it puts this string into the RAM block. And then now I'm arbitrarily erasing that buffer that I want to write to, and I timed it. So it takes about 23 milliseconds, 24 milliseconds to do that erase. And then I write it out. That takes 1/4 of a millisecond to write that out. And then I read back that flash, and we see that that is stored there. Again, this is just for playing and experimenting. Do be careful. If you write below the 0.5 megabyte point, you'll probably have your program crash. So
what RAM is it that you're writing to there? Is that cog memory or is it hub memory?
Well, this RAM buffer is in hub memory. This is all running in spin, so I don't have any cogs running except the spin interpreter. Now I have a serial cog too, but this RAM that I'm showing here is this buffer right here. So I modified my little dump routine so I can tell it if I'm dumping RAM or I'm dumping from flash. You'll see if the source is flash, then I read a byte from this is flash, and it's reading from it. Otherwise, I'm reading from my page buffer that address. So I can look at both. Again, this is kind of it's not advanced, in this scheme of things, but this is something as a tool to play with. As I say all the time, you got to play, you got to work and experiment with things. This I wrote as a program to experiment because I had that client application where I had to figure out how to erase flash and write to it. I went with the simplest possible scheme in that mode. Longer term, though, as Chip was saying, I want to have a file system. Mike is working on one, so I may not have to do anything. But the point is that we have, as Chip pointed out, we have 16 megabytes of storage for less than $1. When I was first out of the service, Radio Shack was selling 5 megabyte hard drives for $5,000. So it's crazy the amount of storage we get for pennies now. But this object gives you read and write capability of the flash, and it does it as fast as I think you can do it without resorting to running an assembly cog. I'm using inline assembly combined with the Smartpins to give me the best possible throughput. So the difference is, as we saw with the other programs, the start method, you'll have to specify a clock speed. So in this particular case, I'm running 20 megahertz SPI clock. And I think the device can go faster, but with wires and other things, I kept it somewhat tame.
Well, JonnyMac, let's switch over to questions, see if anybody has any quick questions, because we've been on for a couple of hours. Don't want to wear you out. We need you tomorrow too.
I have a question.
Yes.
You mentioned you did the laser tag where was an application that you used to read and write to the flash. What are some other applications that you use like this?
My first application writing to flash wasn't even a P2 application. It was a target for a shooting range, a target motion controller, and that was on the P1. On the laser tag, the first version, the P1 version, the P1, as you may, if you've used it, it takes 32K for program space. So I put a 64K EEPROM in the design so that I could write to the upper 32K the parameters about the laser tag weapon. The reason for that is that as a system, the application was so big I couldn't fit it into one program. So in the P1 version of that project, there is also an SD card. And so in that particular laser in that laser tag, there's a configuration program, there's a player program, and there's a referee program. So instead of trying to jam that into one application, which wouldn't fit, because I did try, I broke it up into those 3 elements and then pre-compiled them and put that onto the SD card. And so when you turned on the laser tag weapon, there's buttons on the weapon for selecting things in the display. By holding different buttons down, it would, every application knew to look at those buttons on power up, and it could read the file off of the SD card, put it into the EEPROM, because writing to an EEPROM is pretty easy, and then it would reboot and you would have that application. The nice thing is with 512K of memory and spin and the propeller in general, the P2 is so efficient from speed and, the number of instructions to do a given thing. It's interesting. I was joking with my pal at the laser tag company yesterday. I said, the P2 is kind of like Hollywood. The richer and more famous you get, the more people give to you, that you don't have to buy. So the P2, now we have all this memory and speed, and yet it's so efficient that it's almost as if we don't need all of that. Now, I'm glad we have it. Don't get me wrong, because the new version of the laser tag will fit nice and tightly into a single application, and we don't have to do this load up thing from the SD card. In fact, we're getting rid of the SD card because nobody used it the way we anticipated they would, other than us. And so one of the things that I'm going to be experimenting with tonight after dinner is playing WAV files out of the flash, because I can store all the sound effects for the weapon in the flash and then just play them out of there. I don't need an SD card to read.
Yeah, that thing is way more reliable. There's no mechanical issue, and the access time is deterministic. Whereas the SD card has its own mind, and it has to do its own housekeeping, and it varies by manufacturer, and it's very complicated.
Yeah, we were, that was well, it still is for the company that makes that weapon. They have to buy, they have to be very careful about whom they buy SD cards.
Oh, yeah. It's a problem. Hey, do you know, this is off topic, but how do I get code to appear in the forum? We used to do like code in square brackets, and that doesn't seem to work anymore. I'm trying to put up something for Mike Green that he asked about.
Yeah, I don't know. I heard
still the same way.
Something about that.
The code still works.
Oh, what? Say that again. Sorry.
I said the code still works. At least it did the last time I posted something.
Okay. Okay. I mean, it should be code in square brackets, and then afterward you put slash code in square brackets.
Correct. Is there a C in the toolbar, Chip, that you can click on that should give you the?
No, not yet. I know Michael just got all this reorganized, and he was up for days on end. Ken, do you hear what we're saying? Ken?
Yeah, I do, and I don't know the answer, but I know there's like a couple of ways you could do it. It recognizes the markup language.
Right. There was a note in the forum, upgrade notes and things that are broken. That they were switching between Markdown and the bulletin board formatting. And I think the last note was that he switched it back to the bulletin board formatting by default, and they're looking in how to handle that more permanently.
Okay.
If you look in the discussions, there's a what's broken thread.
Okay.
And it's referenced there. Not that the answer is there necessarily, but at least you see there they caused a bit of issue there when they accidentally flipped.
But there's still posts that are there from a while back that have properly formatted code in them, right?
Mm-hmm.
Yes. Yes. And so it was actually doing a mix of both by what he was saying, which was interesting.
I know we can't get into the old messages when you like quote someone. You used to be able to tear them apart and narrow it down to some point, but now it's like a black box.
There are ways. We just have to relearn the tool.
Yeah, but nothing I can do on my end. We have to reconfigure it. I don't have any control at the level I'm working at.
Well, Micah will be up in about 2 hours, so Send him a
Well,
message.
he needed to sleep because I was talking to him until 1 a.m. his time.
Oh my.
We were going over the RAM, the 32 megabyte RAM thing for the.
Okay, so any more questions for JonnyMac? Because he mentioned an important project. We want him to save his energy tonight.
Well, the Jim's discussion got me kind of going, and I thought, oh, hey, I'm gonna do that. So, for those that are interested, because again, I live and work in Hollywood. Sound effects are a big deal. Jim Bagley has, if those that don't know, he and Chip created an 8080 emulator for the P2, and are running old school games on it that used to run on an 8080. Now they're running them on the P2 and doing really neat things. So for sounds, what Jim did is capture the sounds as wave files, and he's playing them through the DACs. And I've actually, it's not
He
here.
was also re-encoding them to specific bit rates too, as he was.
Yes.
Yep.
Well, and that's what I wrote a little program last night that's working where it'll open the header of the wave file and it'll tell me the bit rate and how many channels and the bit depth. I'm going to see if I can write a little bit of PASM code that will deal with anything, that I get. But for the laser tag, I mean, there are times when putting restrictions is important. So for the laser tag, we always said, look, it has to be a mono file because we only have one little tiny speaker on the device, and you should encode it to 32 kilohertz or lower, and as a 16-bit file. That way I knew I had to read 2 bytes per sample. But I noticed when I loaded up one of Jim's file into my program, he's doing 1 byte per sample. So that presents a different, the 16-bit value is signed, the 8-bit values are unsigned. So I'm going to see if I can figure out a clever way to deal with that and play 8-bit or 16-bit files.
John, you just reminded me of the question I had for Chip that's related to code. May I?
Please.
The spin modulus operator, do you expect it to work on negative values?
There's an unsigned version, Stephen.
Is there?
Yes.
In spin?
Yes. In spin, it's +// gives you unsigned modulus.
Okay. I was using the signed modulus and it was bypassing the negative values. And I was chasing that for a couple hours.
I think my PRNG object is in the downloads folder. If you look in that, I use the unsigned modulus. It makes things easier.
Oh my gosh, yes. Thank you for pointing it out.
Sorry, Chip, didn't mean to steal your...
No, that's all, I'm done.
I was just using that last night, so I was remembering.
And JonnyMac, should we have another session in 2 weeks?
Yes, I've already started on Serial, and I have an Inkscape drawing of Carol's robot. Now it's kind of a blocky looking kind of thing, but the goal for that, so I'm probably going to get myself in trouble, but here's the thing, I'm going to put myself under pressure so I can deliver, is to have, because I don't have a bunch of pings that I want to hook up and be playing with. So I'm going to use my multi-channel ADC, which Ken has been experimenting with, to read 5 potentiometers, and those will simulate Carol's pings on her robot. And then if all goes well, then you will have a screen on the running through processing. See, got another big thick book on it. Nice. And you'll see the arcs of the distance, that are, again, we're spoofing it with the things. But then what I'm also going to try to do, Carol, is add a 6th pot that when you turn it, it turns the wheels on the screen. Now, so I should ask, so I can more closely match your robot, did you just steer with the front wheels or did you do front and back steering?
No, I used Ackerman steering on it, which is just front wheels.
Okay, then I'm just going to do that if I can. Pings, I'm not too, simulating the pings, I don't think I'm very worried about. The nice thing is, so for those that, I mention it all the time, one of my favorite tools to use is Inkscape, this drawing tool that I used. And it creates a type of vector file called SVG, or scaled vector file, and processing allows vector files as objects, so you can bring it. So I'm hoping that'll let me draw. Like I looked at the picture of Carol's robot, kind of did an imaginary top-down view. Again, it's really simplistic, but the idea is to create a tool to simulate what Carol was doing, and then to think, okay, what other kinds of things can we do? The idea is, remember, we're going to be talking about serial, is we're transmitting data over to this application and then displaying it in interesting ways. Now, hopefully by then, we'll also have the Propeller tool upgraded with all of Chip's fancy debug windows, because that's really what's going on. Chip is sending high-speed serial data to a specific window that is displaying data in interesting ways. So we'll have that. The reason for doing the processing project is to then blow that up into custom things. So again, I'm modeling Carol's robot just because it was there. But there's all kinds of other things that one could do. Like Ken loves the weather stuff. So, you know, he could actually do a little bar chart, or, you know, a scrolling chart thing with the temperature and humidity to see what's going on in his office during the day. Fun
Go
stuff.
ahead on yours and use differential steering, because Ackerman steering is a real bitch.
Again, this is just showing, the idea is to show what's happening. You know, for those that like space as much as I do, there's a new rover going to be landing on Mars very soon. And remember, you know, we can't see what's on Mars. So they have to send us a radio data, and then we paint pictures on a screen. So in a way, this is going to be, you know, the John and Carol mini Mars project. We're getting data back, you know, although we're sending it from the Propeller and then displaying it on processing. But you know, if you think about that, I don't know if you had an RF connection on your robot. I assume you did, Carol. You know, you could send the data via radio, the serial data, and display it. So it could be around the corner, but you could still know what's happening. Again, that's the idea, to have some fun, because serial is straightforward, but we can have fun with it and do useful things.
Actually, I believe I was using XBs on that.
It's okay. It's a type of serial connection.
Yep.
Okay, then we'll draw this one to a close. JonnyMac, thank you.
Thank you, everybody.
You've given us a lot to work with, and I'm going to keep playing tomorrow until the email backlog's just too big.
I see some new people, which is really, I'm happy about that. So I'm easy to get. You've got my email address. So I prefer mostly, though, let's keep it in the forum so that everybody gets the answer. But if you need to contact me offline for something, you know, go ahead. So anyway, I want to be available to everybody. I appreciate you taking the time to spend with us today.
Thanks, John.
Okay, guys. Have a great night, everybody.
Bye now.
Bye, all.